Hello, we're going to talk about enthalpy. This is the second lesson of the distance learning grade 12 university chemistry course. So let's jump right in. We're going to talk about three different ways to represent enthalpy. The first is write in a thermochemical equation. So you would write a balanced chemical equation just like in grade 11. But depending on if the reaction is exothermic or endothermic, heat is going to be a product or reactant. So here's two examples. The first example here, you have hydrogen gas and oxygen gas combining to create water and releasing 571.6 kilojoules of energy. That is an exothermic reaction. It has released energy has exited the system, where here you have a decomposition reaction where you have put heat into the system to create the oxide and carbon dioxide gas, and that is an endothermic reaction. Heat has entered the system. So in exothermic, heat is a product, or enthalpy is a product, and in endothermic reactions, enthalpy is a reactant. The example that we have here is from a calorimetry experiment. So there's a video posted that talks about what calorimetry is, and you can go through that. But essentially, the student who's done the experiment has figured out that 0.25 kilojoules per gram is the specific heat of solution of potassium bromate. Specific heat of solution means that when you dissolve a solid into a sample of water, that is the heat that, in this case, is endothermic, that has entered the system. The question is, calculate the molar heat of solution and write it in a thermochemical equation. If 0.25 kilojoules per gram is used, you take the molar mass of 167 to get just your kilojoules per mole. Since this is our chemical reaction, it would be 1 mole of solid potassium bromate dissolving to be 1 mole that is now aqueous, and that endothermic heat physical change requires 42 kilojoules per mole. If you had a reaction where there was a coefficient in front, then you would have to multiply this value by that coefficient so that your chemical reaction, notice here it's just kilojoules and here it's kilojoules per mole. You have to keep the units, be careful with the units to make sure that they're accurate. The second example, use the following thermochemical equation to calculate the molar heat of combustion. Here you have 2 moles of hexane there combusting and giving off 7,086 kilojoules. Since it says molar heat of combustion, you're going to take that exothermic enthalpy value divided by 2 so that you get the kilojoules per mole of every hexane molecule that is combusting. Second method, so you can write the enthalpy not in the chemical reaction, but beside it as a delta H value, a change in enthalpy that has happened due to the written reaction. Exothermic values will have a negative enthalpy, and endothermic reactions will have a positive enthalpy. Here are the two examples before. We have just removed the actual numeric values from the thermochemical reaction and put them to the side and say that the delta H of the reaction is either negative or positive enthalpy based on if it's exothermic or endothermic. A third method is using a potential energy diagram. So this is a graphical representation of the energy transfer. Exothermic reactions, you're going to have the products lower in energy, and in endothermic reactions, you're going to have the products higher in energy, because energy has been gained or lost by the system. Some examples are shown here, where you just show the start and stop levels. There's no actual full progress of the reaction shown in those examples, whereas here, you see the activation energy. So this would be the energy throughout this reaction. Up here, you're in a excited transition state where the hydrogen or oxygen gas have split their diatomic molecule but not fully formed the water molecules yet, and thus higher in energy. And then as soon as those water molecules are formed, some heat has been released, and the delta H of this reaction would be negative because you start at a higher value than you finish at. Activation energy here is from where you start to where you need to reach. And if you're going in the forward reaction, then that would be true to have a higher activation energy in a endothermic reaction than you would in the reverse exothermic reaction, because you start in the exothermic reaction at a higher energy. The difference between the activation energy here would be the energy that is absorbed or released, depending if it is endothermic or exothermic.